So now we're ready to define a lattice. So let S together with some relation R be a poset, and let the elements A and B be in the underlying set S. Then this poset is a lattice if every pair of elements A and B has both an infimum and a supremum. Okay, so we'll look at an example using, once again, the poset consisting of the positive integers with the relation divides. And this poset is a lattice. So first of all, we know that the positive integers with the relation divides is a poset. So let A and B be any two elements in the set of positive integers. Then the infimum of the two elements A and B, as we have just demonstrated, is the greatest common divisor of A and B, which, because A and B are positive integers, they are non-zero elements, and so there does exist a unique greatest common divisor of those two elements, and so the infimum exists for these two elements. And the supremum of the elements A and B is the least common multiple of A and B. And once again, since the elements A and B are positive integers, they are non-zero, and so there does exist a unique least common multiple of A and B, and so the supremum exists. So for every pair of elements in the set of positive integers with the relation divides, each of those elements has both an infimum and a supremum, and so this poset is a lattice. Now, one thing to point out convention-wise, I wrote that the infimum of the elements A and B was the greatest common divisor, but to be more technical, this should be the set consisting, the infimum of the set consisting of the elements A and B. But by convention, we simply write the two elements. So this is by convention. And the same is true for the supremum. The supremum of the set consisting of two elements A and B, we simply write as the supremum of A and B. Again, by convention. Okay? So, new definition. Let the set L together with some relation R be a lattice and let the elements A and B be in the set L. We denote the supremum of the elements A and B by A logical OR B, and call the logical OR the join of A and B. And we denote the infimum of the elements A and B by A logical and B, and call the logical and the meet of A and B. So in the context of a lattice, rather than write supremum A and B, we write A join B, and rather than write infimum of A and B, we write A meet B. And as we will see when we start looking at algebraic structures, binary algebraic structures, the join and the meet are binary operations defined on the set L, where it is understood that it has this relation R that makes it a lattice. And so, as it is a lattice, the supremum and infimum of any two elements does exist for each of the elements. And as we will see, it is a binary operation in that when we perform this operation on the two elements, it is once again in the set L. So there's a preview into some algebraic structure. Okay, so we're ready to look at equivalence relations. As we will see, an equivalence relation is an abstraction or generalization of what we call equality. A relation R on a set S is an equivalence relation if it is reflexive, symmetric, and transitive. So notice that the property that distinguishes an equivalence relation from a partial ordering is the property of symmetry. A partial ordering is anti-symmetric, but an equivalence relation is symmetric. All right? Now, the most often used symbol to denote an equivalence relation is the symbol for similarity. So be aware that the symbol for similarity denotes an equivalence relation. All right? So let this relation be an equivalence relation on a set S. The equivalence class of the relation that contains a particular element S in the set S is the set, which we denote bracket S. And this is a set of all elements X in the set S such that X is equivalent or related through an equivalence relation to this element S. The elements of the equivalence class bracket S are said to be equivalent. or stated slightly in a different way, if bracket S is an equivalence class, of the relation on a set S, then any element in the equivalence class, bracket S, is called a representative of the equivalence class. All right, so we'll look at an example. So let the set S be the set of all polynomials with real coefficients and if f and g are two such polynomials, define f to be related to g if and only if f prime is equal to g prime, that is the derivative of f is equal to the derivative of g, first derivative. Then this relation is an equivalence relation. And we will prove that. First of all, since f prime is certainly equal to itself, we have that f is equivalent to itself, so the relation is reflexive. Second, let f and g be two polynomials with real coefficients, and suppose that f is related to g, then by definition f prime is equal to g prime, and so by equality g prime is equal to f prime, and this is just another way of saying by definition, that is g is related to f. So if f is related to g, then g is related to f, hence the relation is symmetric. Okay, third, let f, g, and h be polynomials with real coefficients, and suppose that f is related to g and g is related to h. Then by definition, we have that f prime is equal to g prime, and from the second relation we have that g prime is equal to h prime, and so f prime is equal to g prime, which is equal to h prime, and so f prime is equal to h prime, and that is f is related to h. And so the relation is transitive, and therefore the relation is an equivalence relation. Okay, so in this same example, the equivalence class of the relation that contains a given function f is the set of all functions g in the set S, such that g is equivalent to the function f. Now, by the definition, this means that g prime is equal to f prime. So g differs from the function f by some constant, where c is a real number. And so the equivalence class containing the function f is the set of all functions g in the set S, such that g is different from the function f by a constant c. A fact, well-known fact from first-year calculus, or first semester calculus for that matter. Okay, so new definition. A partition of a set A is any collection of sets A sub I for I in some indexing set I. A collection of non-empty subsets A sub I such that two conditions are met. One, the union of these non-empty sets A sub I is the entire set A, and two, the sets in the collection are mutually disjoint. That is, A sub I intersected with A sub j is empty for every I not equal to j in the index set I. All right. So a partition of a set is a collection of non-empty subsets that are mutually disjoint and whose union is the entire set. Okay. So we're ready to prove a theorem. So let the relation be an equivalence relation. On a set A, then the following are equivalent. 1. The equivalence class containing the element A is equal to the equivalence class containing the element B. Now, getting ahead of myself. A is equivalent to B, is the same as the equivalence class containing A is equal to the equivalence class containing B. And this is also the same as the intersection of the equivalence class containing A with the intersection of the equivalence class containing B is not empty. Okay, so we're proving that these statements are equivalent, so we'll prove a chain. We'll prove that the first statement implies the second implies the third, and the third implies the first, completing the chain, and therefore the three are equivalent statements. So let A and B be in the set A, and suppose that A is related to B. Then if an element X is related to A, because the relation is an equivalence relation, then X is related to B, again, since the relation is transitive. So the equivalence class that contains the element A is the set of all elements X in the set A, such that X is related to A. But we have just demonstrated that this is the same, or that X is related to B through the equivalence relation. And so this is the equivalence class containing the element B. So the first statement implies the second. So now, suppose that the equivalence class containing the element A is equal to the equivalence class containing the element B. Then the element A itself is in the set which contain the set which is the equivalence class containing the element A. Since A is certainly related to itself, it is an equivalence relation, so it's reflexive. And so, in particular, the equivalence class containing the element A is not empty. So, as the element A is in the equivalence class containing that element, which is equal to the equivalence class containing B, both the equivalence class containing the element A and the equivalence class containing the element B, these both contain the element A. And so the intersection of these two sets is not empty, since they contain at least one element, and that is the element A. And so the second statement implies the third. So we'll complete the chain and show that the third implies the first. So now suppose that the intersection of the equivalence class containing the element A with the equivalence class of containing the element B is not empty. Then there exists some element X of naught in this intersection. So as this element is in the intersection, it is in each of the equivalence classes. So as X of naught is in the set, which is the equivalence class containing the element A, which is the set of all elements in the set A that are equivalent to A, we have that X of naught is related to A, or is equivalent to A. So by symmetry, or the symmetric property, we have that A is related to X of naught. So as X of naught is in the equivalence class containing the element B, which again is the set of all elements X in the set A, such that X is related to B, we have that X of naught is related to B. So by transitivity, we have that A is related to B, or is equivalent to B. Since X of naught is related to A, and, correction, A is related to X of naught, and X of naught is related to B. So the third statement does imply the first. Now, if you have never seen this technique of proof for equivalent statements, we have proved a chain, or really a cycle of implications. The first statement implies the second implies the third, and the third implies the first. So by completing this chain, any one of the statements is equivalent to the other, or any one of the statements implies the other.